Hello everyone, I'm Ze from UNSW Water Research Center. I'm very pleased to be here today and to present some works I did during my PhD. Thanks to my supervisors, Ashish Sharma and Fiona Johnson for their support. I also would like to thank ARC and DPRE for their funding support. My topic today is about a new method and algorithm which is based on variance transformation in the frequency domain. So, why do we need this spectral transformation for ENSO forecasting? Here is one of ENSO indices, ENO 3.4. It has the warm and cold phases. These two phases typically occur every few years with varying intensity and duration. We now look at it in the time domain. So, how does it look like in the frequency domain or spectral domain? Well, first, there are many ways can be used to characterize the frequency domain, like Fourier transform or wavelet transforms. And here we adopt the wavelet transform. Using the same ENO index as our example here, after wavelet decomposition, the original time series can be disaggregated into a group of subtime series, from high frequency to low frequency. Fine scale information is at high frequency level, representing fast-changing details. Large-scale information is at low frequency level, representing slowly changing approximations. Look at those decompositions. Most of the information or variance concentrates at level 4 and level 5. Just to note that the y-axis they are same. If we plot the distribution of the variance by percentage across these levels, we will see a pattern of variance distribution in the frequency domain. The largest variance is at the frequency level 5, equivalent to a period of about 2 years. Our study also shows that two phases of ENSO, El Niño and La Niña, swings back and forth every 2 to 8 years on average. ENSO is our target response in this study, and one of its predictor variables commonly used is the zonal wind stress. For the wind stress, compare with ENSO, how does it look like in the frequency domain? Similarly, applying the wavelet transform, its information or variance are evenly distributed across the spectrum. Again, if we present their variance distribution in the frequency domain, you will see that they have completely different patterns. The main message here is that predictors and response, they can have very different spectral properties. A simple regression model might not work well for this type of system. So we need transformation in the frequency domain to account for this difference. And we proposed the following hypothesis. If the spectrum of the predictor is similar to response, the predictive model will have better accuracy. Now the question is there an optimal variance transformation in the frequency domain? The answer is yes. What we have found is that the variance in the spectrum of predictor X needs to be redistributed according to the covariance C between predictors with the decompositions R and the response Y. In the end, using linear regression model as a predictive model, we can obtain the minimized RMSE using the transformed predictor X dash. And if you are interested in mathematical derivations, you can find more details in our published paper at WRR. So, how does it look like after the optimal variance transformation using the same predictor wind stress showed earlier as an example? The blue bar presents the variance distribution after the transformation. Now the variance concentrates more at medium frequency, level 4 and level 5, and it does become more similar to our target response. While in the time domain, the transformed predictor, blue line here, are much more smooth because the variance at high frequency levels are modulated by our variance transformation. Now, what's the implication of the variance transformation for the ENSO forecasting? Let's wait a moment, since there is a problem we need to address before this method can be used for forecasting. As I mentioned earlier, we adopt a wavelet transform, more specifically, discrete wavelet transform, to characterize the spectrum of variables. And the problem arises from the mathematical basis of discrete wavelet transform, because it requires future information in the decomposition. For example, we have a signal along the timeline, and t is the present. When we calculate the decomposed time series at any given time step, it needs the information from the past, the current, and the future. However, in reality, the future information is not available. This is okay for applications like statistical downscaling, but it cannot be used in the forecasting. So, can we generalize this method to also apply in a forecasting context? The answer is yes. There are classes of wavelets that can allow for this. Those do not depend on the future information. One of them is called maximum overlap DWT, and we have included this in our another paper at EMS. It also comes with an open source R package called WASP, Wavelet System Prediction, which can be downloaded from our school website. The link is also given here. Another important extension of our method is to consider multiple predictors in the system. Let's say, for ENSO forecasting, predictors often include the wind stress, sea surface, and subsurface temperature variables. Previously, the variance transformation refined the predictor spectral representation corresponding to the response individually. So, can we generalize this method to account for existing predictors in the system? The answer is yes. Based on variance transformation, we introduce stepwise variance transformation. The difference between VT and SVT is whether the variance transformation is based on existing predictor variable, for example Z, in the system. So, we combine the variance transformation with input variable selection, such that the stepwise variance transformation can do the spectral transformation and identify significant predictors step by step. Now, I will use a system with one response, Y, and three predictors, x1, x2, and x3, as an example to show how the algorithm works, and what is the difference between VT and stepwise VT. First, we start with a model without any existing predictor, so Z is an empty vector for now. Then we do the variance transformation to obtain transformed x1, x2, and x3. At this stage, VT and SVT transform predictors. They are same because Z is empty. Next, identify the most significant predictor using metric like correlation, R-square, or dependence, and assume x2' is selected. It is the same for VT and SVT model. Then we do the transformation again to obtain transformed x1 and x3. Now VT and SVT transform predictors, they are different because there is an existing predictor x2' in the system. Next, identify the most significant predictor from the remaining predictors and assume x3 is selected for both VT and SVT. Although it is the same predictor variable identified, their values are completely different. Then we continue to do the transformation and selection. VT and SVT transform predictors will be always different, except for the first identified predictor. Now it is time to apply the proposed method to a real example. In the ENSO forecasting example, the target response is NINO 3.4, and there are 30 predictor variables, including zonal wind stress, sea surface, and subsurface temperature from 3 different regions and at different depths. This is a retrospective experiment. First, we obtain transformed predictors using variance transformation. Second, identify the significant predictors. For stepwise variance transformation, these two steps are done simultaneously. Last, we split data into 2 parts, first half for training and the second half for testing. Start from January 1994. We predict next 24 months NINO 3.4 index every month. Coincidentally, VT and SVT identify two significant predictors, region 1 zonal wind stress and subsurface temperature at 100 meter depth. So for the first identified predictor, the zonal wind stress, VT and SVT model, they are same. The transform predictors are smoother than original time series, since high frequency information or noise has been modulated. This is the same example I showed at the very beginning. The second predictor of VT and SVT model are different, since the predictor from SVT model is transformed based on the residual of subsurface temperature conditioned on the wind stress. Look at their y-axis. They have completely different ranges. But anyway, come back to the question, what is the implication of the variance transformation for the ENSO forecasting? Let's look at the key result. We have evaluated two metrics to assess the forecasting scale, correlation and RMSE. There are two important messages here. First, VT and SVT model are better than STD model, which stands for the model without transformation. And SVT is the best among three models. Second, scales of VT and SVT model decays much slower than STD model when the lead time increases. Forecasting scale decreases sharply with increasing lead time. This is a long-lasting issue in forecasting applications, and our method provides a possible solution to address it. Finally, some conclusions. We propose a unique variance transformation in the frequency domain. This is a generic method come with open source tools. Although the application I have done so far mainly in hydroclimatology, potentially it can be used in many other fields like ecology, environment, or economics. In our another paper published at GeoEdge, it summarized all the developments we have made so far for the spectral transformation, including this ENSO forecasting application as well. Again, the WASP package is available from our school website, and it is submitted to Korean as well. If you are an R user, you can easily install and use it with your computer. I also developed a MATLAB version of WASP, which can be downloaded from my GitHub page. That's all. Thank you for listening.